Welcome to this lecture on linear dependence, linear independence of vectors. We also discuss linear span and basis of a vector space. Having got the basic idea about a vector space and a subspace, let us define linear combination of vectors. If one is able to express a vector as a sum of scalar multiples of other vectors, then it is said to be a linear combination of other vectors. For instance, let B and C be two vectors having components 1, 2, and 3, 4 in the two-dimensional Euclidean plane. Then the vector A, 11, 16 can be decomposed as 2 times 1, 2 plus 3 times 3, 4. So therefore we have expressed the vector A as 2 times vector B plus 3 times vector C. So this is the basic idea of a linear combination of vectors. Now formally, if v1, v2, etc. vn are vectors in a vector space V, then for scalars c1, c2, etc. cn, the vector A is equal to c1, v1 plus c2, v2 plus cn, vn, etc. is called a linear combination of the vectors v1, v2, etc. vn. The scalars c1, c2, etc. cn are commonly called the weights. Now, after the definition of linear combination, let us get into a very crucial concept of linear span. Formally, let V be a vector space and S consists of the vectors v1, v2, etc. vn, which is a subset of V. We say that S spans V if any vector, small v, can be written as a linear combination of the vectors in S. That is, we should be able to write any vector V in the space as c1, v1 plus c2, v2, etc. cn, vn. Then we say that the set S is spanning the vector space V. Now let us see a small illustration. Consider this set 0, 1, 1, 1, 0, 1, 1, 1, 0 in the space R3. We say S will span R3 if we are able to express any vector as a linear combination of these three vectors. So suppose we consider a random vector 2, 4, 8 in R3. Let us see if we are able to write 2, 4, 8 as a linear combination of the vectors of S. So let us set up 2, 4, 8 is equal to C1 times the first vector 0, 1, 1 plus C2 times the second vector 1, 0, 1 plus C3 times the vector 1, 1, 0. So we set up a system of homogeneous equations and estimate the values of C1, C2, C3. So hand calculation gives the values 5, 3, minus 1 for C1, C2, C3. So therefore, we are able to express 2, 4, 8 as a linear combination of the vectors 0, 1, 1, 1, 0, 1, 1, 1, 0. This can be justified by finding the rank of the matrix obtained by the three vectors given in S. And if you find it is a full rank or non-singular, then we can say S spans R3. After having seen what is span, let us talk about the very important concept of linear dependence and linear independence. Suppose you are given vectors v1, v2, etc. vn in a set S, which is a subset of the vector space V. Set up the homogeneous system c1, v1 plus c2, v2, etc. cn, vn is equal to 0 and estimate the values of c1, c2, etc. cn. If one finds that c1, c2, etc. cn are non-trivial solutions, that is at least one of them is non-zero, then the vectors v1, v2, etc. vn will form a linearly dependent set. On the other hand, if the coefficients c1, c2, etc. cn are all simultaneously 0, the vectors v1, v2, etc. vn are called linearly dependent. Now you can graphically visualize linear dependence and linear independence. Suppose we are in the R2 space and we have two vectors u and v. If they are non-coincident vectors, then we say the vectors u and v are linearly independent. Otherwise, if they are coincident, then the vectors are linearly dependent. To illustrate, let us look at a couple of examples. Suppose we consider the set consisting of 1, 1, 3, 4, 0, 2, 3, 1, 4, 0, 0, 2, and we want to check the linear dependence or independence. So set up the equation C1 V1 plus C2 V2 plus C3 Vc equal to 0. In this case, the zero vector is the four-dimensional zero vector 0, 0, 0, 0. Set up the simultaneous equations and then try to find the rank of the coefficient matrix. When we find the rank of the coefficient matrix, we find it's a full rank. And once it's a full rank, then C1, C2, C3, and C1, C2, and C3 can be found to be trivially zero. Therefore, the given set of vectors is linearly independent. In the second example, we are given three vectors in a set 1, 2, 3, 3, 5, 7, 5, 9, 13. And then following the same procedure, this time we find that the coefficients C1, C2, and C3 are not trivial. They have non-zero values. Therefore, the given set of vectors is linearly dependent. Once having covered linear independence, linear dependence, and span, there comes the very important concept of basis of a vector space. A set B of elements in a vector space is called a basis if it not only spans the space, but all the vectors of this set B are linearly independent. So a basis is a subset of a vector space which has two characteristics. One, it should span the space. Number two, all the vectors inside this subset are linearly independent. Now, the intuitive idea behind basis of a vector space is that once you have a basis in hand, then you will be able to build any vector with these basis vectors, and you can practically build any vector using this basis. Now, among all the bases, an orthogonal basis has got very valuable features, because if you can have a basis but you cannot use it for an application, then such a basis may not be of any value. But by an orthogonal basis, if we can orthogonalize all the vectors, that is, if we can make all the vectors mutually orthogonal, then it can be useful to build a skeleton for a new coordinate system. So in mathematics, an orthogonal basis has a very, very important significance. So you can see in these diagrams that we are seeing in the first figure the standard basis for the R3 space. You know, in the R3 space, the standard basis vectors are 1, 0, 0, 0, 1, 0, 0, 0, 1 in the directions of the positive x, positive y, and the positive z axis. Observe that all the three vectors are mutually orthogonal. Sometimes in object recognition problems, the standard basis may not be convenient. So we may have to create new basis vectors, which are again mutually orthogonal. So in order to do that, one technique is to rotate the existing vectors, set of vectors, through a rotation process. For example, in the second figure, you can see along the x-axis we have got 1, 0, along the y-axis 0, 1, which is a standard orthogonal basis for R2. By giving it a rotation by a certain angle theta, then we can have new vectors which will also be mutually orthogonal, and that is what you are seeing by those inclined lines. So in this particular lecture, we have tried to understand the basic definition of linear combination of vectors, linear span, the definitions of linear independence and linear dependence, what is a basis for a vector space, and what's an orthogonal basis, and the importance of an orthogonal basis.